Please let me know. Can you please tell me if I'm audible? Okay, so today we'll be discussing some problems related to LP spaces. I hope you all are going through the theory lectures. Okay. So let's start with first question. Question number 1, A part. Show that fx equals to 1 by root x belongs to the space L1, 0, 1. So can you check? Solution. We know that a function belongs to L1, 0, 1 if the integral 0 to 1 fx dx is finite, mod fx dx. So now integration 0 to 1 mod fx dx is equal to 0 to 1, 1 by root x, because always root x is positive. And this is equal to 2 root x 0 to 1, which is finite. Therefore, this function belongs to L1. Part B. Show that fx equals to e to the power minus x by x. This does not belong to L1 space defined on 0 to infinity. So on the interval 0 to infinity, e to the power minus x is bounded. We know it is between 0 and 1. E to the power minus x. So this part will not create any problem. The problem will be created by the function 1 by x. We know that 1 by x blows up near 0. Near 0 it tends to infinity, and that will affect our integral. So let us see how this is affecting. Solution. For x between 0 and 1, we have 1 by e less than e power minus x less than 1. And 1 by x, for x less than 1, 1 by x is strictly greater than 1. For x strictly less than 1. So this gives us our function fx, which is e power minus x by x. This is strictly greater than 1 by e. Or in fact, this is greater than 1 by e times 1 by x. So this implies the integral 0 to 1 mod fx dx. In fact, we can start with infinity. Now this is obviously greater than equal to integration over 0 to 1 because 0 to 1 interval is a subset of 0 to infinity and mod fx is a positive function. This is greater than equal to 0 to 1 mod fx dx, which is equal to 0 to 1 e to the power minus x by x because this is a positive function. And we know that this can be written as limit epsilon tending to 0, epsilon to 1 e power minus x by x dx. By first, this is greater than strictly greater than limit epsilon tending to 0, epsilon to 1 by e times 1 by x dx, which is equal to 1 by e is just a constant. This is limit epsilon tending to 0. Integration of 1 by x is ln x, epsilon to 1. And this is 1 by e ln limit epsilon tending to 0. Log 1 is 0 minus log epsilon. Now, this is equal to 1 by e limit epsilon tending to 0 ln 1 by epsilon. Because this we have the property that log x to the power k is just k times log x. So this minus 1 goes inside, it becomes epsilon to the power minus 1. Thus we get ln 1 by epsilon. Now as epsilon tends to 0, we know that 1 by epsilon tends to infinity. And since log x is increasing function, something like this. Something like this. So this implies ln 1 by epsilon tends to infinity as epsilon tends to 0. So since the smaller function is going to infinity, the larger one will also must also go tend to infinity. This gives us 0 to infinity mod fx dx is not finite. This tends to, since limit epsilon tending to 0 ln 1 by limit epsilon tending to 0 ln 1 by epsilon is infinity. So therefore, the function fx equal to e power minus x by x does not belong to L1. I hope this solution is fine. If you have any doubt, please let me know. If not, we can move to next question. Question number 2. Part A. Suppose P, Q, and R are some real numbers greater than 1, such that 1 by R is equal to 1 by P plus 1 by Q. If N is a sequence that converges to F in LP, and Gn is a function that is a sequence of functions that converges to G in LQ, then show that the sequence Fn Gn, this is just multiplication, Fn times Gn, converges to Fg in LR. So basically we will be using the generalized Helder inequality in order to show this convergence. I'll just recall. Generalized Helder inequality. It states that if P, Q are greater than 1 are such that 1 by Q plus 1 by P is equal to 1 by R, and if where with F being a function in LP and G being a function in LQ, then F times G belongs to LR, and the LR norm of F times G is less than equal to the LP norm of F times LQ norm of G. So we'll be using this generalized Helder inequality in order to prove this convergence. That is, when Fn converges to F in LP and Gn converges to G in LQ, we must have F in Gn converging to Fg in LR. Solution. So let's start with the LR norm of Fn Gn minus Fg. We need to show that this converges to 0. Now this, I can write it as Fn Gn minus Fgn plus Fgn minus Fg. Just adding and subtracting same term, LR, or I'll just write as subscript R for the LR norm. This is less than equal to Fn Gn minus Fgn, just the triangles inequality, Fgn minus Fg R, which is equal to, just taking out common, Gn LR norm plus F times Gn minus G LR norm. Now since all of the Fn's are in LP and F is also in LP, therefore Fn minus F is a function in LP, and we are also given that G is in LQ, then by generalized Helder inequality we get Fn minus F times Gn is a function in LR. Similarly, F times Gn minus G is also a function in LR, therefore these norms are well defined, and hence by generalized Helder's inequality, this is less than.
Screen is not visible.
Screen is not visible.
Yes.
Wait a second. Is it visible now? Is my screen visible now?
No.
Is it not visible to everyone? Because in my other system it is visible. Maybe you can check your internet connection. And who else is in the class? Navina, can you tell me, is it visible? Is it visible now?
No visual.
Wait a second, let me leave and join again.
It's visible now.
Okay. Yeah, can you see my screen?
Yes, yes.
Oh, okay. So we'll be using generalized Hölder inequality. So this is less than equal to Fn minus FLP norm times LQ norm of Gn plus FLR norm times Gn minus G का LQ norm. So this is LP. Now since Gn is a convergent sequence in LQ, therefore it is bounded. So we can find some constant m such that this is less than equal to some m times Fn minus Fp plus Lp norm of F times LQ norm of Gn minus G. Because Gn is convergent in LQ, hence there exists some m positive such that norm Gn Q is less than equal to m for every n and n. Now, since Fn converges to F in Lp and Gn converges to G in Lq, this goes to 0 as n tends to infinity. Since Fn goes to F in Lp and Gn goes to G in Lq. So therefore, this implies Fn goes to Fg in Lr. So I hope this is fine with everyone. If you have any doubt, please let me know. Okay. Let's move to its part B. If Fn converges to F in L2 and Gn converges to G in L2, then show that limit n tending to infinity, integration fn gn is equal to integration fg. So basically, we are again in the same setup. In this case, we have specific p, q, and r. We have p and q to be equal to 2, since 1 by 2 plus 1 by 2 is equal to 1. So using the standard Hilbert inequality, we can prove this convergence. Solution. Mod fngn minus integration fg. This is equal to mod fngn minus fg, which we know it is less than equal to, we can take the modulus inside, fngn minus fg. Now again we will add and subtract fng. So this is fn gn minus fng plus fng minus fg, and then by triangles inequality, this is less than equal to integration fngn minus fng plus integration fng minus fg, which is mod fn gn minus g plus mod fn minus f mod g. Now by Hilbert's inequality, this is less than equal to L2 norm of Fn times L2 norm of Gn minus G plus L2 norm of Fn minus F times L2 norm of G. Now again, since Fn is convergent in L2, this term has an upper bound. So this is less than equal to m times. This is nothing but L2 norm of Gn minus G plus L2 norm of G times L2 norm of Fn minus F. Again, since Fn converges to F in L2 and Gn converges to G in L2, this goes to 0 as n tends to infinity, because Gn converges to G in L2 and Fn converges to F in L2. Therefore, we get limit n tending to infinity, integration Fn Gn is equal to integration Fg. This was just a specific case of the above problem. Next, we will see when we have convergence in LP and L infinity space, then also we get F and Gn to be convergent. Let's move to part C. If Fn converges to F in LP and Gn is a bounded sequence, in L infinity, that means Gn infinity now is less than equal to m for every n in L. With pointwise convergence, Gn converging to G almost everywhere. Everywhere. Then show that integration, or I'll write it as Fngn converges to Fg in LP. So this time we have one sequence converging in LP, the other one being bounded and is convergent almost everywhere. In that case, we get convergence in LP space. Solution. Now consider the LP norm of Fngn minus Fg. Again, I'll be adding and subtracting Fgn and then using the triangles inequality. I'll get this is less than equal to Fngn minus Fgn LP norm plus Fgn minus Fg LP norm. Now, let me take this as I1 and this as I2. I1 to the power p, this is integration Fngn minus Fgn power p. Now this is equal to integration mod Fn minus F power p mod Gn power p. Now since Gn are bounded, the sequence Gn is bounded in L infinity, I can write this to be less than equal to m times integration mod Fm to the power p times integration mod Fn minus F to the power p, which is m to the power p norm Fn minus F to the power p. And since Fn converges to F in LP, this tends to 0 as n tends to infinity. So this implies I1 goes to 0 as n tends to infinity. Similarly, if I show that I2 also goes to 0, then in that case, F and Gn converges to Fg in LP space. Now, I2 to the power p, this is integration. I take F to be common, mod F to the power p, mod Gn minus G to the power p. Now we'll be using the dominated convergence theorem. Since mod Fx to the power p mod Gnx minus Gx to the power p, this goes to 0 because we have pointwise convergence almost everywhere. And the other part we need is the upper bound, the dominating function Fx to the power p mod Gnx minus Gx to the power p. This is less than equal to mod Fx to the power p mod Gnx to the power p plus mod Gx to the power p, some constant terms. We have used the fact that a plus b to the power p is less than equal to some constant times a to the power p plus b to the power p. So this, now since Gn is bounded in L infinity and Gx is just the pointwise limit of Gn, so I can write it less than equal to some alpha times mod Fx to the power p, which belongs to L1, since f belongs to LP. This implies integration mod f to the power p is finite. This implies mod f to the power p. This belongs to L1. And hence by dominated convergence theorem, this implies by dominated convergence theorem, which states that if we have pointwise convergence and an upper bound, which is independent of n, and in L1 space, we get convergence of the integral. Integration mod fx to the power p mod gnx minus gx to the power p, this will converge to integration 0, which is 0. So this implies I2 to the power p converges to 0 as n tends to infinity. Therefore, norm fn gn minus fg LP norm goes to 0 as n tends to infinity. That is, fngn converges to fg in LP space. I hope the solution is fine. If you have any doubt, please let me know. Otherwise, we can move to next question. Question number 3. A part. If Fn converges to F in LP space, then show that for any epsilon positive, measure, this mu is it denotes the measure of the set S epsilon goes to 0, or I should write it as, for any epsilon positive, measure of the set of all those points x such that fnx minus fx is greater than equal to epsilon. This goes to 0 as n tends to infinity. Solution. Let S n epsilon, it's just the notation, be the set of all those points x such that fnx minus fx is greater than equal to epsilon. So this implies, we know that we can write measure of any set to be equal to integral over that set of the function 1. This integral gives us the measure of the set S and epsilon. I'll just multiply and divide by epsilon to the power p. Now this, on the set S and epsilon, we know that epsilon is less than equal to mod fnx minus fx. So I can write it as less than equal to 1 by epsilon to the power p times S n epsilon mod fnx minus fx to the power p dx, since mod fnx minus fx is greater than equal to epsilon on S epsilon n. Now this is obviously less than equal to, since S n epsilon is the subset of, we can write it as set of all points. Suppose the domain is whole x, it's in x. Obviously, this is a subset of x. So this is less than equal to 1 by epsilon power p integration over x, because S and epsilon is a subset of x, and modulus fnx minus fx to the power p, this is a positive function, and this is actually the LP norm of fn minus f to the power p. And since Fn converges to F in LP, this goes to 0 as n tends to infinity. Therefore, for any fixed epsilon positive, measure of the set S n epsilon goes to 0 as n tends to infinity. I hope this is fine. Okay, so let's move to its part B. If Fn converges weakly to F in L2 and norm Fn L2 norm converges to norm L2 norm of F, then show that Fn converges to F strongly in L2. That means if in L2 space we have weak convergence plus norm convergence, then that implies strong convergence. Solution. Let's start with the L2 norm of Fn minus F square. This is equal to integration mod Fn minus F square, which is equal to mod Fn square plus mod F square minus 2 Fn F. Now this is L2 norm of Fn square plus L2 norm of F minus 2 times integration Fn F. Now this term tends to norm F, L2 norm of L2 norm of F. This is what we are given. This is a constant, so obviously this will also go to norm L2 norm of F. And since Fn converges weakly to F, this implies for in L2, this implies for every G in L2 star. Now L2 star is L2 star, which is equal to L2 only because 1 by 2 plus 1 by 2 is equal to 1. So its dual space is itself. We have Fn integral Fng should converge to integral Fg. That's what weak convergence gives us. So, and now since F belongs to L2, this implies integration Fn F should converge to integral F square. So, which is L2 norm of F. So, this implies Fn minus F L2 norm square, which is equal to L2 norm of Fn square plus L2 norm of F square minus 2 times integral Fn F. This converges to F L2 square plus F L2 square minus 2 F L2 square, which is equal to 0 as n tends to infinity. This implies Fn converges to F in L2. Hence, if we have weak convergence and norm convergence in L2 space, that will give us strong convergence in L2. I hope this is fine. Okay, so let's move to next question. Question number 4. For every natural number n, we define a sequence of functions fn to be equal to characteristic function defined on the interval n to n plus 1. Now, this characteristic function gives value 1 whenever x belongs to the interval n to n plus 1 and 0 elsewhere. So this implies if we plot our sequence of functions, the f function f1 gives 1 from 1 to 2, rest 0. This is our f1. Then we have f2 will give value 1 from 2 to 3, rest it's 0. Similarly, so this is f2, then we will have f3 and so on. Show that the sequence fn can never converge in L1R. Cannot converge in L1R. Not even weakly. Converge weakly in L1R. Solution. Let if possible, the sequence converges to some function f in L1. Let if possible, there exists some function f in L1R such that fn converges weakly to f in L1R. That means for every g in L1 star, we know that L1 star is L infinity, integration gfn should converge to integral gf as n tends to infinity. And obviously that limit should be unique. We will show that for different values of values of g, for different functions g in L infinity, we will get different limit. So now if I take now if g belonging to L infinity is such that it has compact support, that means it is 0 outside a compact set. Compact support this implies obviously there will exist a natural number large enough such that after that point f gx is 0, such that gx is 0 for every x greater than equal to n, because in R we know that every closed and bounded set is compact. We are saying that it is 0 outside a compact set, that means it is 0 outside a bounded set. That means there will exist some stage, it can be large enough such that after that the function g will be 0. So this implies integral over R, so minus infinity to infinity, gx fnx, if I take n to be greater than capital N, this should be equal to n to n plus 1 gx fn x, this will be 0 because this is 0 for every n greater than equal to n, because gx is 0 in interval n to n plus 1 for every n greater than equal to capital N. This implies integral over r gfn converges to 0. So therefore, one possibility for the weak limit is 0. Now, but if we take g to be constant function 1, obviously this belongs to L infinity, or we get integration over r gf nx dx. So this is n to n plus 1, 1 dx. Otherwise, f is 0. So this is n for every n in n. So this implies integration over r gfn converges to 1, which is never equal to 0. Hence, by contradiction, fn does not have any weak limit. This gives us a contradiction. And hence, there does not exist any f in L1 such that fn converges weakly to f in Lr. I hope this solution is fine with everyone. If you have any doubt, please let me know. If not, let's move to next question. So we'll again be looking at the same sequence, its convergence in other spaces. We have seen that in L1 space, we cannot have weak convergence, implies we cannot have strong convergence as well, because if we had strong convergence, that would imply weak convergence, which is not there. Therefore, in L1 space, we don't have either weak or strong convergence. So let's look at what happens in the other spaces. Question number 5. Let Fn be the sequence as in equation number 4. Show that Fn converges weakly to 0 in L2 0 to infinity. That means for every g in L2 star, which is L2, integral Fng should converge to 0. This is what we need to show. Let's see. Solution. Let g belonging to the L2 0 to infinity star, which is equal to L2 0 to infinity, be arbitrary. And this implies 0 to infinity f gx times fnx. This is just n to n plus 1 gx times 1, because fnx is 1 in n to n plus 1, and otherwise it's 0. Now, using Hilbert's inequality, this is less than equal to integration n to n plus 1 mod g squared to the power 1 by 2 1 square n to n plus 1 to the power 1 by 2. Now, since g is in L2, this integral is finite. So this is less than equal to L2 norm of g. And this integral, it's nothing but just 1. This is n plus 1 minus n to the power 1 by 2. This is we need to show that this goes to 0. So I'll take this to be less than equal to integral n to infinity. Obviously, n to n, the interval n to n plus 1 is a subset of the interval n to infinity. G square to the power 1 by 2. And this is nothing but just 1. This is integral n to infinity mod G square to the power 1 by 2. Now, this is tail of a convergent integral. So we know that tail of a convergent integral converges to 0 because integral 0 to infinity mod G square, this is finite. This implies n to infinity mod G square is just the tail. The way we have for the case of series, similarly we have an integral tail of a convergent integral goes to 0. 0 as n tends to infinity. So basically the measure over the set where we are integrating, this measure is going to 0. So therefore the sequence Fn converges to 0 in L2 weakly. Therefore Fn converges weakly to 0 in L2 0 to 1. I hope this is fine. If you have any doubt, please let me know. Okay. Let's see what happens to the sequence in the space L infinity. Question number 6. Let Fn be the sequence as in question number 4. Show that Fn converges in weak star topology, converges in weak star to 0 in L infinity 0 to. So in weak star topology, we have Fn, the sequence converges in weak star to F in V star if and only if Fnx converges to Fx for every x in V. So firstly, the weak star convergence is in the dual space. Now we need to show the convergence, weak star convergence in L infinity, which is dual space of L1. So our V will be L1 and V star will be L infinity. Solution. If Fn converges to 0 in weak star topology in L infinity 0 to 1, which is the dual space of L1, this implies Fng this converges to 0 for every g in L1 0 to infinity, and this notation is actually fn integral fn g. That is integral fn g converges to 0 for every g in L1 0 to infinity. So this is our claim. We claim that this integral converges to 0 for any g in L1. So now for any arbitrary g in L1 0 to infinity, modulus, so this integral is 0 to infinity fng. This is obviously less than equal to, we can take this integral, this modulus inside fng. Now fn is the characteristic function on the set on the interval n to n plus 1. So this is integral n to n plus 1. And on the interval n to n plus 1, the value of function fn is 1. So this is just modulus g. Now since this g is in L1, this is again less than equal to n to infinity mod g. And this is a tail of a convergent integral, because g is in L1, so integral 0 to infinity mod g is finite, so this converges to 0 as n tends to infinity, because this g is in L1 0 to infinity implies 0 to infinity mod g. This integral is finite. This implies n to infinity mod g is tail of a convergent integral, hence n to infinity mod g goes to 0. Because obviously the measure of the set on which we are integrating is going to 0. So therefore, we get the weak star convergence. Therefore, Fn converges to F in weak star topology in L infinity 0 to infinity. Hence we are done. I hope this solution is fine. Yeah. So let's move to next question. Question number 7th. A part. Show that every bounded sequence in LP has a weakly convergent subsequence. for every p greater than 1. For this, we recall a theorem that says that if V is reflexive, then every bounded set, or we can say that every closed unit ball, closed unit ball or every closed ball, uh, then closed unit ball in V is weakly compact. That means if V is reflexive and we have a sequence which is bounded, that means it is contained in some ball. If V is reflexive, then that ball will be weakly compact. That means it has a weakly convergent subsequence. So all we need to show is that V is that LP space is reflexive. So by reflexive we mean its star star should be isomorphic to itself. Now we know that LP star is LQ, where Q is such that 1 by P plus 1 by Q is equal to 1. So this implies LP, this is LP star. So LP star star is LQ star, which is LR, where R is such that 1 by R plus 1 by Q is equal to 1. This implies basically R is nothing but P. This gives us star star of LP is LP itself. That means LP is reflexive. That means every closed and bounded set is compact. Every closed and bounded set in LP is weakly compact. This implies every bounded sequence in LP has a weakly convergent subsequence in LP. All we need to do is just recall the fact that if V is reflexive, then closed unit ball is weakly compact. Hence, every bounded sequence must have at least weakly convergent subsequence. If you remember, in finite dimensional spaces, or everything is the space is eventually equivalent to Rn. There we have Bolzano-Weierstrass theorem, which says that every bounded sequence must have convergent subsequence. So in the case of infinite dimensional spaces or any arbitrary Banach space, we cannot confirm. In fact, we it's never strongly convergent subsequence. But if it is reflexive, then we can get at least weakly convergent subsequence. Okay, so let's move to part B. Show that unit ball in L infinity is weak star compact. For this, I would like to recall the Banach-Alaoglu theorem. Let's recall Banach-Alaoglu theorem, which states that if V is a Banach space, then the set B star, which is all those F in V star, such that norm F is less than equal to 1. Basically, the closed unit ball in V star is weak star compact. Now, since L1 is a Banach space and L infinity is L1 star, this implies B is equal to unit ball in L infinity is, this is closed unit ball. So here also it should be closed unit ball. That means we are considering the boundary as well. Closed unit ball. This is closed unit ball in L1 star by Banach-Alaoglu's theorem. B is weak star compact. Weak star compact subset of L1 star, which is L infinity. Therefore, closed unit ball in L infinity is weak star compact. This is fine. So we can move to next question. Number 8. For some n greater than equal to 2, we define a function f at t is equal to t to the power n minus 1 upon 1 plus t squared to the power k. Show that this f belongs to L1 0 to infinity for every k greater than n by 2. That means we need to show that integration 0 to infinity ft dt, since f is positive in 0 to infinity, so mod f is just f. This should be finite for k strictly greater than n by 2. So we'll be using monotone convergence theorem. Let me recall monotone convergence theorem. It states that if fn is a sequence of measurable functions, let fn is a sequence of measurable functions on some measure space X such that it satisfies the following two conditions. Number one, this is an increasing sequence, 0 less than equal to f1x less than equal to f2x, and so on for every x in X. Second, we have pointwise convergence. F in X converges to some fx for every x in X. Then we must have integration over x, fn converges to integral x f dx, or we can write d mu, where mu is the measure on the space X. So we'll be using this monotone convergence theorem. Solution. So in order to use monotone convergence theorem, firstly we should have some sequence. So we'll define a sequence. For every n in N, we define fnt is equal to a function which is equal to t to the power n minus 1 by 1 plus t square to the power k for all 0 less than equal to t less than equal to n and 0 else for t strictly greater than n. So this implies for every t in R, fnt, so as n tends to infinity, this t greater this measure of the set n to infinity goes to 0. So eventually this is converging pointwise to the function t to the power n minus 1 by 1 plus t square to the power k, which is nothing but ft. So this is limit t tending to, n tending to infinity. So we have pointwise convergence. Also, for every 0 less than equal to t less than equal to n, we have fn plus 1t is equal to fnt, because obviously the function is same for up to n, and fnt is 0 in n to n plus 1, whereas fn plus 1t is strictly positive in the interval n to n plus 1. So we have and for t strictly greater than n, or we should write n strictly less than t less than equal to n plus 1, we have fnt is 0, which is strictly less than t to the power n minus 1 by 1 plus t square to the power k, because this is strictly positive, and this is equal to fn plus 1t. And for every t strictly greater than n plus 1, fn plus 1t is 0, which is equal to fnt. Therefore, from all these three cases, we get fn plus 1t is greater than equal to fnt for every t in 0 to infinity. And since this natural number n is also arbitrary for every n in n, therefore the sequence fn is an increasing sequence, and hence we have pointwise limit and increasing sequence. So we can use the monotone convergence theorem. This implies by monotone convergence theorem, integration 0 to infinity ft dt, this is equal to limit n tending to infinity integral 0 to infinity fnt dt. Now fnt is 0 for all t greater than n. So this integral is just from 0 to n. So this is limit n tending to infinity, 0 to n, and in 0 to n, f and t is defined to be t to the power n minus 1 by 1 plus t square to the power k dt. Now I can just multiply and divide it by 2. So I can write it as 1 by 2 limit n tending to infinity, 0 to n t to the power capital N minus 2. Now since n is greater than equal to 2, so this exponent is positive. Thus we have 2t dt by 1 plus t square to the power k. I can take t square to be some x, so we'll get 2t dt to be dx. This is 1 by 2 limit n tending to infinity, 0 to n. So this is x to the power n minus 2 by 2 dx by 1 plus x to the power k. So now I'll split this integral 0 to n between in two integrals, 0 to 1 and 1 to n. This is 1 by 2 limit n tending to infinity, 0 to 1 x to the power n minus 2 by 2 by 1 plus x to the power k. So for x belonging to the interval 0 to 1, this function is clearly bounded, and hence by Riemann integral this is bounded and continuous. So hence by the properties of Riemann integral, this is a finite integral. Plus, and obviously this is independent of n, so this limit will also be constant. This is 1 to n x to the power n minus 2 by 2 by 1 plus x to the power k dx. Now this is equal to some constant times limit n tending to infinity, 1 by 2 integral 1 to n x to the power n minus 2 by 2 by 1 plus x to the power k. Now let's evaluate this integral. Now integration 1 to n x to the power n minus 2 by 2 by 1 plus x to the power k. This is less than equal to, so for x greater than 1, so this is directly less than equal to 1 to n x to the power n minus 2 by 2 by x to the power k dx. Why? Because obviously 1 plus x is greater than x, because x is positive. So its power k will also be equal to greater than its power k. So 1 upon 1 plus x to the power k will be less than 1 by x to the power k. This is greater than 1. Since this is greater than 1, that is why we got the same inequality. Otherwise, the inequality would have been, no. In that case also, yeah. So this is equal to integration 1 to n x to the power n by 2 minus k minus 1 dx. Now this is equal to x to the power n by 2 minus k 1 to n if this exponent is not equal to minus 1. That means n by 2 is not equal to k. And obviously we need to show the convergence for k strictly less than n by 2. So we already have this not equal to n by 2. So this is equal to n by 2 minus k. This is equal to 2 by n minus k, n to the power n by 2 minus k minus 1. So therefore, this integral 0 to infinity ft dt this is less than equal to some constant times limit n tending to infinity 1 by n minus k n to the power n by 2 minus k. Now this will be finite only if the power of n is negative, because if it's positive then the limit will blow up to infinity. So this is finite for n by 2 minus k. This should be less than equal to 0, or k should be less than equal to n by 2. But also for k equals to n by 2, we had a problem, so this should be strictly less than. So therefore, f belongs to L1 0 to infinity, or k strictly less than n by 2. Sorry, greater than. This is greater than. I hope this solution is fine. It's nothing but just integral. We need to see is that where this how for what power of n this limit is finite. That was the only thing. Otherwise, it's just basic integration. Okay, so let's move to next question. Question 9. Let x s mu be a measure space um, let 1 less than p q r less than infinity be such that 1 by q is equal to alpha by p plus 1 minus alpha by r for some alpha belonging to open interval 0 to 1. Suppose there's a function u that belongs to LPX intersection LRX, then show that this function u belongs to LQX as well, and its LQ norm is less than equal to its LP norm power power alpha times its LR norm to the power 1 minus alpha. So again, we'll be repeatedly using the generalized Hölder inequality to prove this. Solution. We have 1 by q is equal to alpha by p plus 1 minus alpha by r. So this can be written as 1 upon p by alpha plus 1 upon r by 1 minus alpha. So this gives us 1 upon p by alpha q plus 1 upon r by q1 minus alpha is equal to 1. Just multiplying both sides with q. And since p by alpha q is greater than 1, because obviously since 1 by q is equal to alpha by p plus some positive term, that means 1 by q is greater than alpha by p. which gives us P by alpha Q is greater than 1. Similarly, since 1 by Q is greater than 1 minus alpha by R, this gives us R by Q, 1 minus alpha is greater than 1. So, this gives us R by Q, 1 minus alpha is greater than 1. So these two terms are greater than 1, and the sum 1 upon P by alpha Q plus 1 upon R by Q, 1 minus alpha is equal to 1. So we can use Hilder's inequality. Let's mark this as 1. Now, since U belongs to LPX intersection LRX, this implies integral x mod U to the power P. This is finite. I'll write it in such a way so that this belongs to some let's see. So this is mod U to the power alpha Q to the power P by alpha Q. This is finite. So this gives us U to the power alpha Q. This belongs to L P by alpha Q x. Here. So we'll try to find some power of U that will belong to L R by Q 1 minus alpha. Similarly, integral over x mod U to the power 1 minus alpha Q to the power R by Q 1 minus alpha. This is nothing but integral mod U to the power R, and since U belongs to LRX, this is finite. So this tells us U to the power 1 minus alpha Q. This belongs to L R by Q 1 minus alpha x. Now we need to show that U belongs to LQ. So let's start with integral over x mod U to the power Q. I can write it as mod U to the power alpha Q plus, times mod U to the power 1 minus alpha Q. Now I'll be using Hilder's inequality by first. So this is less than equal to mod x mod U power alpha Q. So our exponent is P by alpha Q. So this is P by alpha Q times alpha Q by P times integral over x mod U to the power 1 minus alpha Q. So its conjugate was R by Q1 minus alpha to the power Q1 minus alpha by R. By Hilder's inequality, since 1 upon P by alpha Q plus 1 upon R by Q 1 minus alpha, this is equal to 1. U to the power alpha Q belongs to U L P by alpha Q, and U to the power 1 minus alpha Q this belongs to I did some mistake. So L minus alpha Q, this belongs to L by R Q times L R by Q 1 minus alpha x. Now this gets cancelled out, this gets cancelled out. So this is equal to LP norm of U to the power alpha Q times LR norm of U to the power Q times 1 minus alpha. Now, since U is in LP and LR, this is finite. Therefore, norm U LQ is finite, and norm U LQ, which is equal to integration x mod U power Q to the power 1 by Q. Now, this is less than equal to 1 by Q power of this term. So, this is mod U LP to the power alpha times norm U LR to the power 1 minus alpha. Therefore, get norm UQ is less than equal to norm UP to the power alpha times norm UR to the power 1 minus alpha. That is what we wanted to prove. Therefore, if P, Q, and R are such that 1 by Q equals to alpha by P plus 1 minus alpha by R for some alpha in 0 to 1, if U belongs to LP and LR, then immediately we get U belongs to LQ, and this is the relation between the norms. I hope this is fine. We have mainly used the Hölder's inequality and the condition given on the terms on the real numbers PQR. I hope this is fine. If you have any doubt, please let me know. Okay. So let's move to next question, the last question for today's session. Question number 10. Let f from R to R be uniformly continuous function if f belongs to L1R, then show that it converges to 0 mod fx goes to 0 as mod x tends to infinity. That means if the function is uniformly continuous and integrable, then it should go to 0 as mod x tends to infinity. So that means at infinity it is vanishing. Solution. So let if possible, it does not go to 0. Let if possible, mod fx is not going to 0 as mod x going to infinity. That means we can find or we can construct a sequence xn such that xn is going to infinity, but mod fxn is strictly greater than epsilon for every n in n. Now let's use the property that f is uniformly continuous. Now, since f is uniformly continuous, this implies for above epsilon positive, there exists some delta positive such that mod f x minus fy is strictly less than epsilon by 2 whenever mod x minus y is less than delta. So this implies mod fx, this can be written as mod fx plus mod fxn minus fxn. This is greater than equal to mod fx minus mod fxn minus fx xn, because we know that mod a minus b is greater than equal to mod a minus mod b. Mod fxn, we know that it is greater than epsilon, and mod fxn minus fx is less than epsilon by 2, so its negative is greater than epsilon by 2 whenever mod xn minus x is less than delta. So this is strictly greater than epsilon minus epsilon by 2 whenever mod xn minus x is less than delta. This implies mod fx is strictly greater than epsilon by 2 for every x belonging to delta neighborhood of xn, and this happens for every n in n. So we'll be taking delta such that all these bxn deltas are distinct. This implies for every n in n. Since we are in R, so this is just the interval xn minus delta to xn plus delta. We are in R. So this integral xn minus delta to xn plus delta mod fx dx is strictly greater than epsilon by 2 xn minus delta to xn plus delta 1 dx, and this is nothing but epsilon times delta, because this integral will be basically 2 delta. So taking delta small enough so that taking delta small enough. Obviously, if something holds for big delta, it will hold for the smaller delta as well. So we'll be taking delta small enough so that all these intervals xn minus delta, so xn minus delta to xn plus delta, intersection xm minus delta to xm plus delta, this is empty for every n not equal to m. So basically we were taking xn to infinity, so our terms were something like this. So we are taking delta such that these intervals all are distinct. Obviously, since we are going to larger, we can find this delta. So this implies integration minus infinity to infinity mod fx dx. This is obviously greater than equal to summation n from 1 to infinity integral xn minus delta to xn plus delta. So because the union of these intervals is obviously less, is a subset of R. This is, and we know that this integral is strictly greater than epsilon times delta. So this is strictly greater than epsilon times delta times summation n from 1 to infinity 1. And since the series tends to diverges to infinity for any epsilon delta, we get f does not belong to L1R, which is a contradiction to our assumption because it was given in the problem itself that f is in L1. But since f belongs to L1R, we get a contradiction. Therefore, mod fx should converge to 0 as mod x tends to infinity. We are done. I hope this proof is fine. If you have any doubt, please let me know. Okay, then, if there's no doubt, you can leave the class. We'll meet next Friday. Hopefully, uh, we'll discuss some more problems. Okay, then. Thank you.